Hello friends, in the previous few lectures we have been thinking about the components that are necessary to describe the mechanical condition experienced by any region within 2 and 3 dimensional material when exposed to both uniaxial and triaxial tensile loading. So we saw that when the consideration or when the focus was just a 2-dimensional setup and we had a specific region of interest that was inclined, then we saw that the mechanical condition and how to describe it under uniaxial tension, we needed two components, one a normal stress component and a tensile stress or tangential stress component. And when we moved to 3 dimension under uniaxial tension, we saw we needed 3 stress components, one normal and 2 tangential or shear stress components. Now in the previous lecture we saw that when we impose rather a triaxial tensile loading in all the 3 directions, there is a tensile acting on a 3-dimensional material, then we realized that in such a case we needed 9 components of stresses to define or to describe the mechanical condition experienced by a specific region within the 3-dimensional material. So when you have a 3D system or a 3-dimensional system experiencing triaxial loading, then the components of stresses that are necessary in order to describe its mechanical condition can be written something like this. So this would be a normal stress or along the direction or along the z direction. This would be 2 shear stresses acting along the z plane, and similarly you would have the normal components or normal stress components acting along the y and x direction and the corresponding shear stresses. And we saw that these are the 9 components of stresses that are required to describe the mechanical condition of a material or a region of a material when it is in 3D, when the system is in 3 dimension and it's experiencing triaxial loading. And we saw that there are certain stresses or certain shear stresses, to be more specific, that are equal to one another. So you can reduce those, and when you talk just about independent stress components, you just need 6 independent stress components to describe the condition experienced by a section in the 3-dimensional material experiencing triaxial loading. So if you write down these 6 components, you will have the 3 normal stress component and 3 shear stress component. Now let's try to build on it. So under triaxial loading and for a 3-dimensional setup, we saw these are the stress components that you need. The independent stress components that you need are only these. Now let's build on this understanding and see look for a specific case. Let's take this understanding and focus on a specific case. Use this understanding for a specific case. Supposing instead of, in the previous lecture we considered for a 3-dimensional system, we considered a rod that we thought of to be something similar to the tensile testing specimen. So we thought of a rod for our 3-dimensional setup and we used that, and based on this rod we considered a small section in it, a cube section, and then we were able to the reason we chose a cube, or instead of selecting a point we chose a cube, is because it was easy for us to represent the different components of stresses. So that's the reason we represented it in the form of cube. And the overall material that we considered, the cube was a part of our overall 3-dimensional material, which was a cylinder, which we related it to the tensile testing sample. Now in this lecture rather, we will focus on another 3-dimensional material which has its unique form. For that, let us assume our frames of reference. So we have our z axis, we have our y axis or other x axis, and we have our y axis. Now instead of considering a rod, let us consider a plate. So let us assume a plate. So the thickness of this plate is along the z axis, and you have a plate that is extending something like this, or maybe I would use a different color to make it distinct. So this is the thickness of the plate, and pardon me. So you have a plate something like this, and the face of the plate, that is the face of the plate, this region, the face of this plate is perpendicular to the x-axis. So the thickness this is along the x-axis, or rather the z-axis, and the face of the plate, the face, I mean the surface of the plate, is perpendicular to the z-axis. So thickness is along the z-axis, and also the face of the plate is perpendicular to the z-axis. Now this is a three-dimensional plate. So let us assume the dimensions of these plate as something like this. So if you talk about this dimension here, or if you talk about the dimension along the x-axis, let us call that to be Lx, and the dimension along the y-axis, let call that to be Ly, and the thickness along the z-axis Lz. So we have dimension Lx, Ly and Lz. So these are the one dimensional, or rather the dimension of the plate along x, y and z axis respectively. Now if you look closely, it is easy for you to understand that the Lx is very much greater than that of Lz, and similarly the Ly is very much greater than that of Lz. So since we are considering a thin plate, it means the dimensions along x and the y axis are greater than that of z axis. Now this, even though it's a thin plate, now this being a three-dimensional structure, and let us assume there is a triaxial loading acting on it. So this being a three-dimensional structure, even though it's a plate, it is not a rather a cylinder that we previously considered. Even though this is a plate, since it is in three dimension in nature and it is also experiencing a triaxial loading in all the three axes, and tensile loading is acting on it, that means we can represent the stress condition at any point or any plane within this plate by the same 9 components. So let's write down these components. So that would be, as we have previously seen, there will be 3 normal components, or let us for this argument write it separately. So there will be normal components. Normal stress components would be, these would be the normal stress components, and the shear stress components would be these would be the shear stress components, and these would be the normal stress component. Now we have seen that this normal stress component x will be acting in the x direction. So normal stress component x will be acting along the x direction. So this would mean that I will use a different color, blue maybe. So the normal stress component of x, it will be acting along x direction. So this would be the direction of normal stress component, and similarly this would be the direction of the normal y component, and this would be the direction of the normal z component. Now if you notice, when you compare the area that is relevant to this normal stress component y and compare that to the area that is relevant to normal stress component z. So we have a normal stress component x, and this is dependent on a particular area, or this you can write it as P along x, that is the load along x, and the area along, or the corresponding area that is perpendicular. So this would be this area. We are talking about this area for the normal stress component along x. Similarly, when you talk about the normal stress component along y, it would be the load along y and the area and the corresponding area. So that area would be this one. And finally, when you want to talk about the normal stress component along the z direction, then you have to include this whole area. So that means that when you compare this, the area that is relevant to the normal stress component x, so let us write it as nx, and the area that is relevant to normal stress component y, these two areas are considerably less than the area that is relevant to normal stress component along the z direction. It also means when you write the expression for the normal stress component along the z direction, if you assume that the triaxial loading is such that in all the three directions the same amount of, or rather similar loads are being acting and the similar orders of loads are being acting, they are not drastically different from one another, then your expression will be something like this: the normal stress component that is relevant to the z axis, and you can write the similar here. And now since this is very much high when you compare to all the other areas, and also since the ranges of all the difference, it can also be equal, and since instead of restricting ourselves to equal triaxial load, if the ranges are supposed, or let us assume that ranges are almost in the same order, so that means that since this area is significantly higher, so what I am talking about it is, what we are essentially doing is we are comparing this area, this overall surface area, or let me use another color. So the overall surface area or the surface area of the plate with the area that is associated with the thickness. So what you are relating is area associated with the surface of the plate to the area associated with the thickness. So when you compare this area associated with the plate to that of the area associated with the thickness, then you could see the area, the surface area is much more pronounced or much more significant than, so this area, let me show. So this area, the area 1 is much more greater than area 2 and 3. So that means, since the area assumes a place in the denominator, so that means when you compare to the stress along the x and y direction, this stress along the z direction would be insignificant. With relation to the stress along the x and y direction, the stress along the z direction will be insignificant. So that means when you want to represent or describe the mechanical condition in a plate experiencing triaxial loading, then you can get rid of this component here, the normal stress component along the z direction, because you have enormous amount of area when you compare that area to that of the area that is required to calculate the stresses along x and y direction. And since this area is considerably huge, that means the stress acting along the z direction will also be will be less or insignificant. Therefore, instead of 3 components for a plane, you just need 2 normal stress components. So you just need 2 normal stress components. Okay. So now let's go back and focus on see how can we, if we can make a similar simplification for the shear stress components. So we have made, by considering the area that is responsible, that is associated with the normal stress components, we were able to get rid of one of the components, because the area associated with the stress along the z direction was quite large. When you compare it to the other areas, it means the associated stress will be less, and therefore we were able to get rid of it. So let us now consider let's see if we can make a similar simplification for the tangential or the shear stresses. So we write the shear stresses in this manner. So we saw that we need 3 independent shear stresses to describe the mechanical condition experienced by a 3-dimensional material or on which a triaxial load is applied. So we have 3 shear stress components. Now if you take this here, if you take this component here, let us begin by considering the first component, that is xy. So in this shear stress component xy, it means this is acting on the x plane along the y direction. So let us begin by considering. So for considering this shear stress alone, let us redraw the plot. So redraw the plate that we have considered, and so this was the plate that we initially considered. Yeah. So this was the plate that we initially considered. Now when you talk about, so this would be your z axis, this would be your x axis, and this would be your y axis. Now when you talk about x plane, so in x plane what will happen is the way you would define and explain is the value of x will be constant and all the other values of the coordinates. So the value of x will be constant and all the values of other axes or coordinates will vary. So that would mean this is the plane. And the direction along which it is acting is in this direction, in the y direction. So this is what we mean by shear stress x, y. So tau xy is the x, it is acting along the x plane, along the, and the direction is along the y direction. Now the area that is responsible or associated with this particular shear component is the area that has already been highlighted. So this is the area that is associated with the x, that is associated with this particular shear component. Now let us talk about this shear component. So in this shear component, what we have seen is that this is associated with the, or we know that from the way this shear component is described, this is associated with the z plane. So z plane is nothing but the surface of the plate, and that means the area that is associated with this stress is considerably higher. So that means that since this area gets into the denominator part, we can write that tau xy is very much greater than tau zx. So we have done the similar thing what we have done for the normal stress. We have considered the area that are relevant to each of the stress components, and when we see these areas are considerably higher in one case, we can get rid of that associated stress component, because since the area is higher and it gets into the denominator, the resulting stress will be lower. So we can get rid of this one. So we can get rid of this component of shear stress. Now the left is this one, which is tau yz, and we have seen this can also be written as tau zy. So this was covered in our previous lecture, and when we assume that tau yz, or we can arrive at a condition where tau yz is equal to tau zy, then ultimately what we are doing is we are again talking in terms of the z plane. So we are again talking in terms of z plane, meaning the area that is supposed to be considered is also the area of the surface, and it is significantly greater than the other areas. So that means similar to this components of the shear stress, that is tau zx, this component of the shear stress, that is tau yz, will also be significantly lower than tau xy. So ultimately, given these two conditions, so since we have these two conditions here, this one and this one, we can get rid of this component as well. So ultimately, the shear stress component required to describe the mechanical condition experienced by a particular region of interest in a plate is just, we can just define it by xy. So we just need only one shear stress component. So we saw in 3-dimensional triaxial case we need 3 yz, tau zx, we need 3 shear stress component in general case. This is a general 3-dimension triaxial case, we need these 3 shear stress component. However, in case of a plate or a plane, or in case of a plate with a dimension something like this, in case of a 3-dimensional plate something like this, you can get rid of these 2 shear stress components, because the corresponding or the associated areas are quite large, and ultimately the only shear stress component that will be of any significance is this. Now when you couple this with the normal stress component that we have already seen, so we have already seen that in a plate like setup, in a setup wherein you have a 3-dimensional structure that is not a cube, or that is not a rod, wherein you have a simple plane or a simple plate like setup, then you would need only 2 normal stress, and when you combine that to the requirement of only 1 shear stress, so ultimately you only need 3 components of stress, 3 components of stress to represent this, 3 components of stress to represent the mechanical condition experienced by a specific region within a plate. and this plate is experiencing a triaxial loading. So when you have a three-dimensional setup which is a plate and it's experiencing a triaxial loading, this plate is experiencing a triaxial loading. Even though this is a three-dimensional plate, given its size or given its characteristic dimension, the number of components that is required to describe the mechanical condition experienced by a region within this plate is just 3. So we saw when we want to represent the or when you want to describe the mechanical condition experienced by a specific region in a three-dimensional material experiencing triaxial loading, we needed 9 components, and we were able to reduce, or we were able to identify some relation between these shear stress of the components, and we were able to reduce that 9 components to 6 independent components. And now when you take a three-dimensional setup that is similar to that of a plate, wherein the 2 dimensions are significantly higher than 1 dimension and the face has a significantly larger area in other than other sides, it means that your number of components of stress that is required to describe the mechanical condition experienced by a region within that three-dimensional material, again under triaxial loading, is just 3. Now it is also important to understand that, like in case of the plate, it is important to understand that whatever we have been talking so far was in relation to the area. Even though the plate, we defined the plate in terms of the dimension, the way we derived at the 3 components, we were able to get rid of the components that were not that significant. We arrived at in terms of the area, and because these stress components were related to the surface area, which was significantly higher than the other areas, we were able to get rid of this. Now this stress condition associated with the plate is referred to as the plane stress condition. So this has a definite name for it. So this stress condition associated with the plate is referred to as the plane stress condition. So what characterizes this plane stress condition is that when you talk about plane stress condition, the stress along one particular direction is missing. The stress along one particular direction is missing. So that means the shear stress along the particular direction is missing, meaning it is close to 0. And similarly, you can have xz, and similarly you can have yz. So these are the stresses along the z direction. So these are also 0. And since you can write this as something like this as well, zy, you can write this as something based on the z plane. So we were able to get rid of all these rather 5 components, and we were able to express that and get rid of all these 5 components and express the stress condition based on 3 components. So the plane stress condition means the stress along one of the direction is absent. So that is a simplest way of describing the plane stress condition. And the very good example for that is what we have seen, a simple 3-dimensional plate. So the question, if someone poses you like what are the number of components that you need to describe the mechanical condition experienced by a region under plane stress condition, if that is a question posed to you, you can think about a plate and you can say you need just 3 components, and by definition by definition of plane stress, meaning the stress along one of the direction is absent, then you can use this assumption, that is whenever you have a particular direction involved in the stress component, that is 0, and particularly when you talk about shear stress, you can reverse the plane and stress because they are equivalent, and by doing this you will ultimately end up with having just 3 components, and using these 3 components of stresses you will be able to describe the mechanical condition under plane stress condition or under a plane stress. So with this I would like to wind this part of the lecture. This is not the whole lecture, this part of the lecture I would like to wind up, because we will be building on this in the next part of the lecture, and we will try to understand what are the ways ways under which or using which we can describe the direction of these stresses that are involved in the plane stress condition. So let's see ourselves in the part 2 of this particular lecture. Bye.